Hello, geometry friends. Here is a lesson for topic 6 about similar right triangles. So if you are told that you have a right triangle with an altitude, then 3 similar right triangles are formed. Can you see in this picture where there's 3 right triangles? You have the triangle EDC, which is the biggest triangle, and it's a right triangle because it has a right angle at D. Then you have this small triangle from C to D to F, which has a right angle at the point F, and then the medium-sized triangle EDF also has a right angle at F. So there's 3 different right triangles in there, and they are all similar to each other. Remember, we've talked about an altitude before. An altitude is the height of the triangle. It's a perpendicular line drawn from a vertex to the opposite side so that a right angle is formed. So in a right triangle, one of these sides that are perpendicular to each other can count as the altitude. But in this case, there's another altitude drawn from the point D to point F. D is a vertex. It's perpendicular to the opposite side, so that's an altitude here. So when the altitude has been drawn in a triangle, then 3 similar triangles exist in the diagram. And to show you that, it makes sense to look at and compare each angle measure. Now, not every angle is actually this measure. I didn't measure them, but just to kind of use some numbers and apply it to our picture, if you look here and say, okay, well, if I'm going to compare the measure of angle E to angle C, angle E is smaller than angle C. And I know that in every triangle, there's the sum of the 3 angles is 180 degrees. So if I were to just say, let's just assume, or hypothetically, that the measure of angle E is 30 degrees. That means that if angle E is 30 and this whole angle D is 90, then this angle here must be 60. Okay, and now we also know that this angle right here is 90. So that means if this angle is 60 and this is 90, then this angle right here that goes from C to D to F must also be 30. And again, if that angle was 30, hypothetically, and we know that for sure this angle right here, for the one that goes DFE, is 90, that means that this angle right here must be 60. So do you notice how now all the angles that we have are either a 30, a 90, or a 60? And when triangles are when angles are congruent, that means the shapes are the same. That means the triangles are similar. So what I can do is I can write a similarity statement that involves all 3 of these triangles. It might look like this. If I start with the biggest triangle, which I'll name triangle D or EDC. Let's call it that. Let's call it triangle EDC. And in triangle EDC, we have angle E is a 30-degree angle. Angle D, this whole angle D is a 90-degree angle. And then angle C is a 60-degree angle. So this was a 30, then a 90, then a 60. That triangle is similar to another triangle where you have a 30-degree angle, then a 90-degree angle, then a 60-degree angle. So let me go to the medium-sized triangle right here. The 30-degree angle is still angle E. So I'm going to say triangle E. And then the 90-degree angle is the angle F. So angle EF and then D. So triangle EDC is similar to triangle EFD because both the angle E corresponds to angle E, then angle D is 90 corresponds to the angle F that's 90, and C that's 60 corresponds to D that's 60. But then there's one more, the smallest triangle here, where again, if I write it as a 30, then a 90, then a 60, that's called triangle DFC. And so all 3 of these triangles must be similar because all 3 of them have congruent angles that correspond to each other. And when I do that, now I'm not going to need to compare all 3 of them at the same time, but I'm only going to compare 2 of these triangles at one time. So we might compare the small triangle to the medium triangle, or the small triangle to the big triangle, or the medium to the big, just like this. Let me put it in here. I'll put you on pause for a second. So if I was going to compare the small triangle to the medium triangle, that would be triangle DFC is similar to triangle EFD, because again, I match up a 30-degree angle with a 90-degree angle with a 60-degree angle. And the order doesn't matter as long as you're consistent. But then I have a 30, a 90, and a 60. And just like each one of these, I can compare the small triangle DFC to the big triangle EDC, or the medium triangle EFD to the big triangle EDC. So I can compare any two of them, and then I can write my corresponding sides in a ratio if I'm trying to find a missing length. So when I do a problem like this, I have these tools. I can use these similar triangle ratios like I had right here and what we talked about back in topic 5. And then I could also use the Pythagorean theorem, which if you remember what Pythagorean theorem looks like is when you have a right triangle, which we do in this case, we have 3 right triangles. If you know 2 sides of a right triangle, you can always find the third side because they're related in this way, that the length of A squared plus the length of B squared is always going to be equal to the hypotenuse length C squared. So now let's take a look at a couple of these questions and see what the difference is between the two. There's 2 different kinds of examples that we'll look at, and then we'll see how we're going to set up some similar right triangles and solve for missing lengths. So in both of these questions, we're trying to find the length of X. One of them is involving the altitudes, and the other one's involving the sides. So let's take a look at this one first. And the first thing I want to do is just to help me understand what I'm looking at and how these triangles are similar, I'm going to just say hypothetically, let's put in some angle measures. So when I compare these 2 triangles, or when I see in this triangle, so I can see that this whole angle B is a 90-degree angle. Triangle ABC is a right triangle. This segment from B to D is an altitude, okay? And so what I'm looking for is I want to try to set up my similar right triangles and say which are the triangles that are in fact similar. And to do that, I like to match up congruent angles. So when I compare the measure of angle A to the measure of angle C, I think angle A is a little bigger than C. So I'm going to call angle A a 60-degree angle, and I'm going to call angle C a 30-degree angle. And now I'll go ahead and figure out all the other angles that are in here. So if I call angle A 60 and angle C 30, that means that this angle right here has to be 60 from C to B to D, because that's 90. And 60 plus, or 60, 30, and 90 makes 180. And then again, if that's 60 and that's 90, then this one has to be 30. So I always like to just choose 30s and 60s because it makes the easy, it's always simple computation that adds up to 180 very easy like that. So now I'm going to write my triangles that are similar to each other. So the first triangle I labeled as triangle ABC. And once I establish that order, A, B, C, now I have to make sure that I follow the order. So the angle A I said was a 60-degree angle. The angle B of that whole triangle is a 90-degree angle, and then angle C is 30. So I went 60, 90, 30 in this time. So then I got to make sure that the other triangles also have a 60-degree angle first, then a 90-degree angle, then a 30-degree angle, 60, 90, 30. Now, in this triangle, I want to find the length of X, the length of A to D. And I also know that I have the length of the altitude from D to B in this case. So with these numbers, I'm going to compare the small and the medium triangles. So I'm going to just simply cross this triangle off of my similarity statement and just compare these 2 triangles. And so let me go ahead and now write my sides into a proportion using just those 2 triangles. So I have the side AD corresponds to BD, and then DB corresponds to DC, and finally AB corresponds to BC. Now, when I look at my diagram here, I'm going to decide which of these I should get rid of. Okay, and do you notice how in the diagram, this third ratio that compares the length of AB to BC, those are 2 sides that I do not know the length of, and I do not need to know the length of. So that's the ratio that I'm going to cross off. Now I'll just simply replace or substitute the length of each one that I have. So what's the length from A to D? That's the length X. What's the length from B to D? That's 3. The length from D back to B is still 3. And then the length from D to C is 9. So this, now you notice how this segment BD is the same here and here. So this thing called the mean proportional, what that means is when you have a ratio where the bottom of one ratio is the same as the top of the other ratio, that's what a mean proportional is. And so now we're just simply going to solve for the value of X. So if you cross multiply, 9 times x is 9x equals 3 times 3 is 9. So 9 divided by 9 is 1. So there's my length of, or that's the measure of x. Okay, so here's an example involving the altitudes where I'm going to compare the small triangle with the medium-sized triangle. Now, if I'm not using the length of the altitude, instead, I'm going to use only length of one of the sides of that big right triangle. Now I'm going to compare either the small to the big or the medium to the big, and I'll show you how that works here. So the first thing I'm going to do is just guess and say, which of the angles do I want to call 30, which one's 60, and then fill in the rest of them. So if I call angle C 30, that means that angle A has to be 60, and therefore that this angle ABD has to be 30, and its adjacent angle DBC has to be 60. And then I use that to write my triangles that are similar to each other. So I called the first triangle ABC. That was the biggest right triangle where the angle A is 60, this whole angle B is 90, and then 30. So I have a 60, then a 90, then a 30, and I'm going to continue in that order. Then I have angle B of this other triangle is a 60, then a 90, then a 30, and finally a 60, 90, 30. So there's my triangles. Now, in this case, I'm only going to compare the big triangle with one of the other triangles, either the small triangle or the medium-sized triangle, because I want the length, this side CB is both in the biggest triangle and in this triangle BDC. So those are the two triangles that I'm going to compare this time. So I'm simply going to cross off the triangle that is over here. That's this one right here. I only know the length of 15. I don't know the side AB or DB, so I'm not going to use this one. I'll cross off triangle ABD. And now I'm going to write my proportions with those two triangles here. And so I compare the ratio of side AB to BD, and then BC to DC, and finally AC to BC. And when I look and say, which of these three ratios am I not using in this case, notice how I do not know the length of AB or BD. So that ratio right here is the one I'm going to now cross off from here. And then I'll substitute what is left. What's the length from B to C? It's X. What's the length from D to C? D to C is 5. What's the length from A to C? A to C is this whole length. In this case, it'd be 20. 5 plus 15 is 20. And last, what's the length from B to C? Again, it's X. See, in this case, BC, that side, is the mean proportional. That side is the side that's the same on both the top of one ratio and the bottom of the other ratio. And now I'll just solve for x. Now in this case, if you're doing the algebra here, when you multiply x times x, you get x squared is equal to 5 times 20 or 100. So we actually have this this quadratic equation to solve. But if you're using that program, then you could easily solve that way that I showed you back for topic 5. But either way here, what number squared is equal to 100? It's 10. So the length of x has to be 10. And that's how we do similar right triangle proportions. It has to be one of these two cases where you're either comparing the small triangle and the medium triangle, or either the big triangle with either the small or the medium. You're either using the altitude or you're not using the altitude. And that's going to kind of give you some idea of which of the two ratios or which of the two triangles you should use. Bye-bye.